All right. But light is actually how scientists unlocked what the electrons are doing. Okay? So this whole unit is about where are the electrons. We're going to get to how did Bohr come up with his model on Wednesday, and then we're going to take Bohr's model one step further to like the current model of the atom, which is not Bohr's model. It's a little bit different. And so they use light to do this. So it seems strange, but these parallels about light are going to get applied to electrons. So Friday, you read the background about light. Please make sure you have checked your answers. Please make sure you have corrected your answers. Please make sure you ask questions if you don't understand something, all right? But for the background of light, you read about the fact that light exists as what we call a dual form, all right? So light is a wave. Scientists knew that for years, right? We knew that light, so electromagnetic radiation is the fancy word, but as light comes from the sun, it travels as a wave, right? And we knew that forever, okay? And so light has wave characteristics. But then there were weird things that scientists couldn't explain, all right? They couldn't explain why certain metals glow certain colors in a flame. That's what we're going to look at tomorrow. Why if you excite like neon, it glows a certain color in a tube, like neon lights. Why the photoelectric effect happened. There were things that scientists couldn't explain without explaining light as also being a bunch of little particles. Okay? So we're going to have these two pieces of light. You skipped all of the math in your reading. I think you wrote the one equation down, but like you didn't do any of the math. That's what we're going to look at today. And then tomorrow we'll do the lab, and then Wednesday we'll tie it into electrons. It's going to seem crazy. All right, so light. You studied waves and light back in some elementary school class at some point. I don't remember when it is. But light exists on a spectrum. Right? So light is a form of energy, so it's energy. It travels as a wave, and it takes on various forms that you use in your everyday life. All right, we've got radio waves, so if you ever listen to the actual radio in your car, like WEBN or, oh my God, I don't even listen to the radio anymore, what, Q102, they always sponsor things. All right, those are radio waves. I am fairly confident we've all cooked food in a microwave, so microwaves. Infrared is what your body interprets as heat. All right, so the warmth of things is a lot of infrared radiation. What your eyes see as color is a tiny little part of the spectrum. It's called visible light, but those wavelengths of light your eyes interpret as the different colors that exist. You have ultraviolet or UV light. That's what burns you in the summertime. That's why you need to wear sunscreen. You have x-rays, and I'm going to take the assumption we've all had x-rays done before, whether you've broken a bone or you've gone to the dentist. I'm fairly confident we've all had x-rays. And then the very far form of this electromagnetic radiation is gamma rays, which is like radioactivity, which we'll do a unit on at some point probably. And so these all exist. You've been exposed to them your entire life. You're exposed to them because you live on Earth, right? But scientists have exploited them to be able to do things. Microwaves to cook food. Radio waves to listen to different broadcasts, right? So we use it for what we want to do. And so light is, again, we studied light, and it led us to how we're going to look at electrons. But first part of light is it's a wave. So it's got two things we're going to talk about measuring. First is wavelength. Wavelength is the distance between, BTWN is between, corresponding points on adjacent waves. Which is the fancy way of saying the distance from the top of one wave to the top of the next. Right? That's what wavelength is. So here in the picture, all right, you've got two different waves. So wavelength is just the top to the top, top to the top. This picture is short, this picture is longer. That's all they're showing you. And you can measure that distance, okay? It is a length, so the unit will be meters, so M. When we do our calculations, and that's maybe the hardest part of this math. I don't know why every year students struggle with this math. It's really just, here's the equation, plug the numbers in. But you've got to know what symbols represent each thing. All right, but wavelength is going to be in meters. All right. When you do the math, you're going to have to turn it into meters to make sure when you plug it in, it's in the right unit. And inside of our equation, I don't know why they did this, but they did not pick W for wavelength, or L even. We went Greek, all right? So we use Greek letters to represent these, and they use the Greek letter lambda, which is an upside down backwards Y. That's how I call it. But it is the Greek letter lambda. All right? So each of your different forms of electromagnetic radiation, radio waves, microwaves, X-rays, visible light, all have their own unique wavelengths. Shh, we're talking. All right. So they each have their own wavelength. Okay. Second thing for a wave, and again, you wrote these down on Friday and you're reading, you just didn't do any math with them, is the frequency of the waves. Okay. So frequency is the number of waves that pass in 1 second. So if you were to count how many waves are coming, that's what the frequency is. And again, each of your different parts of your spectrum have their own unique frequencies. The radio waves have their own frequency, the microwaves have their own frequency, the color light has its own frequency, X-rays have their own frequency. All right, depending on what the frequency is what we use them for. Right? The unit for frequency, the SI unit, is called the hertz, which we abbreviate HZ. Right? And again, the little picture is there for you to visualize. Right? This top wave is high frequency. There's lots of waves coming. The bottom one is low frequency. Less waves are coming. All right, so you're just literally counting how many waves are coming. Right? Again, when we use it inside of our equations, again, I don't know why they didn't use the letter F. I think they actually do in physics, but in chemistry we don't. We went Greek again, and we're going to use the Greek letter nu, which looks like a fancy V. So you can honestly just say, put a V. I call it the fancy V. When you type it, they look a little more scripted. Right? But these are the two things you can measure about all of your waves inside of the electromagnetic spectrum. Every section of it has a wavelength and a frequency. Okay? And your wavelength and your frequency are mathematically related to one another. So you get your next equation on your back. It's on the back of your periodic table. You don't have to memorize equations ever in here. They're all there for you. But there is a relationship that's going to exist between your wavelength and your frequency. And this is your first equation in this unit. And then we'll do the second one in a second. And the equation is C is equal to lambda times nu. All right? So again, this is your upside down backwards Y. That's your wavelength. That's how it gets typed when it, like, in the font. And it's a little fancier than when I write it. But your wavelength has to be in meters, and the units are going to be really important. All of this time that I keep focusing on them, it's for reasons. Right? This equation requires that you use meters for your wavelength. And then this is that fancy V. That's your Greek letter nu. That's your frequency. And honestly, probably the hardest part is that you just have to know which letter represents what. Right? It's going to take practice. And then the last letter in the equation is the letter C, which stands for the speed of light. And the speed of light is a constant. All right, so it's always the same number. You don't have to memorize it. If you got your periodic table out, it's the bottom left-hand corner on the back side. The speed of light is 2.998 times 10 to the 8th meters per second. So all of the different types of light all travel at the same speed. So whether it's a radio wave or a microwave or colors or UV light, all of the waves travel at the same speed. It's just a matter of how many waves are coming and how far apart are the waves. That's what changes between them. Okay? And we're going to get an inverse relationship. So here's where, yes, you're going to have to do math, but you can also do conceptual questions. So if I increase the wavelength, which means I separate, my waves are farther apart, I will decrease my frequency. That's what it means to have an inverse relationship. When one goes up, the other decreases. And you can look back at the little picture here. This would be increasing my wavelength because from this picture to this picture, there's a bigger gap. So bigger wavelength, lower frequency. Less waves are coming, all right, if you like visual things like pictures. And then vice versa, if you lower your wavelength, you will increase your frequency. So underneath this learning target, while it does say perform calculations, you can also do like relationships based on the equations without doing any real math. Okay? So we'll walk through 2 examples with this equation. There. So it says microwaves are used to cook food and transmit information. What is the wavelength? So I'm going to box what I'm looking for. Done enough problems with me now to know. We're looking for the upside down backwards y. That's what wavelength is represented by. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? There's your fancy V. Okay. And then this is where you just have to know what equation to use. Well, you've got frequency, you want wavelength. This is how they are mathematically related. C equals lambda times nu. Okay. Trickiest part, 1, knowing which symbol represents which thing. Practice that. That's a like memorization kind of thing. 2nd is paying attention to your units. Okay? You cannot plug numbers into this equation unless it's meters or it's hertz. Right? So if you are plugging in frequency, it has to be hertz. So I always do like a little check. I'm in hertz, so we're good. I could just plug it right in. The next example I'll show you where that's not true, so that you see what I mean. Now we'll plug our numbers in. C is always 2.998 times 10 to the 8th. That doesn't change. Meters per second. On the other side, we don't know the upside down backwards y, so we'll leave it as the symbol. Or put an X if you don't like the weird Greek letters. And then times 3.44 times 10 to the 9th hertz. How are you going to solve? Divide. All right. Back to algebra 1. Actually, it's quite like junior high math. So 2.998, second e to the 8th. Use your magic E button again, like for scientific notation. And then divided by 3.44, second comma 9. And you should get a wavelength of 0.0872, because we had 4 sig figs and 3 sig figs. So I'll keep 3. 0.0872. And then what did I tell you was the unit for wavelength?
Meters.
Meters. So there you go. Meters. So the little waves that are cooking the food in your microwave, all right, the little waves that are coming down and hitting your food to get the water molecules to spin and heat up your food. That's how it works. If you looked at their wavelengths, there would be 0.087 meters from top to top. So it's what? 8.7 centimeters from top to top. That's what the waves are that are coming at your food. Right. Yeah.
So do you just cancel out the
Hertz and seconds will cancel, yes. Hertz is technically 1 over seconds, which is why they cancel. Because it's the waves per second. That's why. So yes, hertz and seconds can cancel. All right, we'll do a harder one. I feel like it's plug equations in. All right, so it says objects get their colors from reflecting only certain wavelengths of light when hit with white light. So the color you see on objects is because they're reflecting a certain wavelength at your eye. And then your eye is like, oh, that's green. Or, oh, that's orange. So light reflected from a green leaf, apparently I can't type, is found to have a wavelength of 490 nanometers. All right, so there's your wavelength. What is the frequency? That means we're looking for the fancy V of the light. All right, so I'm just getting used to labeling things, which we've been doing this whole time. And then it says, note, 1 meter equals 1 times 10 to the 9th nanometers. All right, so here's how they're related. C equals lambda times nu. Right? This is what I'm telling you. For the number that I give you, you need to look at the unit. I told you wavelength has to be in what unit? Meters. What's it in here? Nanometers. All right, so we have to convert to meters before you're allowed to use the equation. Okay, that's what I'm saying. To use the equation, you have to be in meters or you have to be in hertz. Okay? I'll give you weirder units, like I won't give you, like I don't expect you to know nanometers. I think centimeters is the only one you still have to know from our first unit. But do your quick little conversion. 490 nanometers. Nanometers have to go on the bottom, and then I gave you 1 meter is 1 times 10 to the 9th nanometers. Fill them in. All right, you've got the equality, you know how they're related, cancel out your units, type in your calculator. You should get 4.9 times 10 to the negative 7th meters. Now you can plug it in. You cannot plug in things that are not meters or hertz. So we'll plug them in. 2.998 times 10 to the 8th is C. We found our wavelength. It's 4.9 times 10 to the negative 7th. And then times frequency. Again, how are you gonna solve? Divide. 2.998 E8 divided by 4.9 second comma negative 7. And I would highly encourage you to use the E, otherwise put parentheses around it. And I got 6.1 times 10 to the 14th. And then your frequency is always hertz. All right, thoughts on plugging into the first equation? Notice that you have a really small wavelength. 10 to the negative 7th is a really small number. Therefore, you get a bigger frequency, right? Small wavelength, big frequency. Here's like a way to tell you're doing the math right. If you're looking for a way to like, did I do my wavelength and frequency division correctly? When you add your two exponents, they should be close to 8. So 14 and negative 7 would be 7. That's close to 8. Like they should be within your 8 as your exponents. And if you did it wrong, you're not going to have that. All right, so I'm like giving you ideas of how to check your work. So that's light as a wave. And scientists knew that. We've known this relationship for a long, 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 long time. All right, that was well established. But there were the weird things about light that they couldn't explain. Why did hot iron only glow certain colors? All right, like why was it only these very distinct colors? All right, so your second equation came from the idea that, well, light actually is also a particle. We call them photons. So there's like a little beam of like particles, like think like tennis balls, flying at you from the light on the ceiling. And they each carry a little bit of energy with them. Right? So your second equation relates more to the fact that they're little particles of light instead of waves. And each little particle of light carries energy with it. It was proposed by this man, Max Planck, or Max Planck, however you want to say it. And these two, energy and frequency, have a direct relationship. So if one goes up, the other goes up. Okay? That should make sense. So frequency is how many waves are hitting you. So the more waves that are coming, a higher frequency, the more energy that's hitting you. All right? So I think your little simulation had like, it opened with the idea of like a ping pong ball versus a bowling ball at the bowling alley. Same idea here. All right? These particles that are flying at you, some of them are tiny, not very much energy. Some of them are large and have lots of energy. Okay? But again, here's your equation of how they relate to one another. Okay? E equals h times nu. So E should be easy, that's energy. Your energy is always in joules, that's the SI unit for energy. From back, you would have done energy back in middle school too. Kinetic energy, potential energy, you did that, I promise you. You already know this letter. That is your frequency of your light. So the frequency of how many waves are coming relates to the energy. And that should make sense because like the more waves that are coming, the more energy you should feel. Think about sitting on the beach on a nice, calm, peaceful day in the ocean, like just kind of casually the waves roll in. That's low energy, low frequency. And then imagine the beach the day before the hurricane hits, but there's lots of waves coming in. That's very high energy. And again, has to be in hertz. And then you get a new letter, but the nice thing about this letter is it's a constant. It's called Planck's constant or Planck's constant, however you want to say his last name, and it's always 6.626 times 10 to the negative 34th joules times seconds. Okay. So this is your second relationship, and this is, I think, what we could get confused on is what do the symbols represent? Energy only relates to frequency. Okay, so to find the energy, you have to know the frequency of your light, all right, which is the little V. And see, that's where I'm telling you, you got to pay attention, label numbers. What symbol do they go with? You have E's, you have V's, and you have upside down, backwards, Y's. Those are your three options. So we'll do an easy one and a hard one. And like I said, tomorrow we'll do your lab, and then you'll have some time to work on your mixed practice. Your next mixed practice, or next CYU set, sorry. Your next CYU set, you only have to do odds to get full credit. But all of you need to think about how much practice do I need individually, right? Maybe you need to do all of them if math is not our strong suit. So it says, what is the energy? So again, I box, I want the letter E of an ultraviolet photon. So it's just a little particle of light. UV light is what burns you in the summertime. That has a frequency of 2.5 times 10 to the 16th hertz. There's your little V. I always label things, okay? The only equation you have that relates for energy is this. E equals H times frequency. Plug in your numbers, all right? Check your unit. Frequency is in hertz, so we're good. That's what it has to be in for all of the math, so we're good there. So we can just plug everything in. H is a constant. Don't memorize it. It's on the back of your periodic table. It is 6.626 times 10 to the negative 34th. And the units are just there to make everything else cancel out. Joules times seconds. Plug in your frequency. 2.5 times 10 to the 16th hertz. How are you going to solve? Just multiply. And I got 1.7, and you will always get very, very, very tiny exponents, 10 to the negatives, because you're calculating one little particle hitting you, but like there's never just one little particle on you. You would always feel more energy than that. But you're calculating one tiny particle of light, and again, in your world right now, there's moles and moles of particles hitting you. There's not just one. And so it's gonna be a very small number every single time. And I'm just trying to give you ideas of like, how can I check that I did it right? And we'll do the hardest they can be. And then you can start working on it, but you'll have time after your lab tomorrow. I just shortened your lab to be a little less questions, so you'll have some time to work on this math tomorrow. Trying to help you out.
Thank you.
You're welcome. Although, you know, you can do some work at home. All right, last example. So it says, argon fluoride, ARF laser, used in some refractive eye surgeries, emits electromagnetic radiation, so light, of 193.3 nanometers. Nanometers is a wavelength. It's meters. There's your wavelength of your light. What is the energy of a single photon of the radiation? Right? So here we're looking for energy, but we were given upside down, backwards Y. All right? So you gotta do some thinking here. Energy is H times frequency. Do we have the frequency? Did I give you the fancy V? No, what did I give you? I gave you the nanometers, right? I gave you the upside down, backwards Y. So you can't just plug that number into this equation. All right, so what you're gonna do with your friends, first thing you gotta do is find the frequency. So you gotta go back to our very first equation and solve for frequency. And then once you find that, what can you do with it? Plug it in. This one's gonna take you 2 steps. So turn to your friends.
Hey guys.
You're gonna do the first equation followed by the second equation. Go.
First equation.
And it's got to be in meters too. You got lots to do here.
It's a bit loud. I think
Yeah.
it's a typo because it says 1 nanometer
Oh.
equals 1 times 10 to the negative 9th meter.
No,
You did that
so
wrong, bro.
Or is that right?
yeah. So there's two ways to look at it. Or there's 1 times 10 to the 9th nanometers in 1 meter.
So it's either?
Yeah.
Oh, okay.
It's just whatever I give you.
Oh, okay.
Yeah, I already made myself a note that maybe next year I would just put them all in the back of the periodic table somehow, all of the conversions, like the prefixes.
Yeah, bro.
Yeah, because I saw the one on like the first question we did and it was
Oh, you're
different.
right.
But it's just a different way of writing it. It's like saying 1 meter is 100 centimeters, or saying 1 centimeter is 0.01 meters.
Okay. And then now I think.
But I will always give you nanometers, so whatever I give you, just use.
Alright.